Hey guys, welcome back to Gluten Free Learning. Today we are doing some numerical methods analysis, and we're going to be looking at some terms that are used in the course. And you might not know what they are, so we're just going to look at matrix condition and matrix norms. So first we're going to learn what it means to say the matrix condition, or what the condition number is, whether it is ill-conditioned or well-conditioned. So given a matrix A times your vector x equals some solution C, some solution vector C. So the condition basically is saying whether it's ill-conditioned or well-conditioned. It says basically, okay, let's suppose we make a small change in A. How will that affect our solution vector? Will we still get a small change, or will we get a large change in C? So if we make a small change in A, does that result in a small change in C or a big change in C? And vice versa. We can make a small change in C, the solution vector, and how will that affect our matrix A? Will we get a small change or a big change? So if we get a small change in A, and that results in a small change in C, we can say that it is well conditioned. Similarly, if we make a small change in A, but we get a large change in C, then we have an ill-conditioned matrix. Let's look at an example. So what is a big change and what is a small change? So if we can say we have some system, some matrix A, 400, negative 201, negative 800, and 401, x1, 2, and this all equals 200 and negative 200. So using Gaussian elimination or whatever technique you want to use, you can use a computer, whatever, this will yield a solution of x1 and 2 equaling negative 100 and negative 200. So now suppose we want to make a small change in A. Let's make a really small change in A. Let's change the 400 to 401 and leave everything else the same. So that is a small change, right? So solving this out, we actually get x1 equaling 40,000, and x2 is 79,800. So we can see that is a very large change. So is it safe to say that this is an ill-conditioned system? Probably, yeah, it is. But there's also one more check that we can do without actually guessing and checking if your solution, how it will react to a small change in your given matrix. You could find what's called the condition number. So the condition number will give you a pretty good indicator of if your system is ill-conditioned or well-conditioned. And it's denoted as cond A, meaning the condition number of A, and if the condition number of A is approximately equal to 1, we can say it is well conditioned. And then if it is much greater than 1, then it is ill conditioned. So how do you go about calculating the condition number of A? We use a formula. Condition of A equals the norm of matrix A infinity times A inverse infinity. So this notation means the norm of A. And this notation is the same, but it just means the norm of A inverse. What is a matrix norm? A matrix norm is basically just the sum of rows, the sum of the row n that you're looking at. So for example, say if we have a matrix A, 1, 2, 0, 1, the norm of A infinity is equal to the largest row sum of our system. So we have to look at both of our rows, add the absolute value, and the larger one is going to be the norm. So we have one here, right? So we add 1 to 2, that got us 3. Then we add 0 to 1, and that got us 1. So the row norm, we could say, is 3 of this matrix. And the little infinity, this notation just says basically the row sum of any row, the maximum row. Okay, so it should be noted that, say if we wanted, the norm of matrix A, and we put a subscript 1, that means that we're just looking at row 1. So that would be 3. And say if we wanted the sum, or the norm of matrix A, row 2, that would equal just 1, because our row 2, the sum was just 1. So in this case, this means the largest of all of the row sums, the norm of the matrix infinity, and in this case it was 3. So coming back to our condition A equation, all we have to do is find the norm of the matrix A and the norm of the inverse matrix A out of any of the rows, because we have the infinity, and multiply them together. So we need to find the inverse of matrix A. So maybe we'll go a little side note here. So if we have a matrix A, to find the inverse, we divide it by the determinant of A, and then we swap these two, the diagonals, we swap the diagonals, and we throw a negative in front of the B and C values. And then this is the inverse of matrix A. So following this formula, our matrix was, let's rewrite it out. So we've got A equals, remember using the 400 now. We're not using the 401. I used the 401 just to show that by making a small change in A gave us a large change. But we're back to using just the 400 in this slot here, because that's the original matrix A. Okay, so the determinant, remember it's just these two diagonals multiplied by each other, and you subtract the other diagonals multiplied by each other. So we got 400 times 401 minus negative 800 times negative 201, negative 400. So A inverse, negative 1 over 400. Remember, swap the diagonals and throw a negative in front of the other diagonals. Therefore, A inverse equals this. Okay, so now we need to find the norms of these matrices, right? So, norm of A, our original matrix, we got a 400 and a 200 in the first row, and we got an 800 and a 401 in the second row. And we know that we're taking the absolute value, remember? So if we got a negative, just take the absolute value. So we can see that the second row is going to give us a larger value. So 801 minus absolute plus absolute of 401 gives us 1201. Good. Now we want to take the norm of A inverse, and same thing, take the absolute values, right? And we're looking at our rows, and we can easily see that row 2 is going to give us a larger number. So absolute of negative 2 plus absolute of negative 1 equals 3. Done. So now we can say condition A equals 1201 multiplied by 3 equals 3,603. So this is the condition number. The condition of A is 3,603. So remember before I said, okay, well, a well-conditioned system is going to have a condition number somewhere close to 1, and an ill-conditioned system is going to have a number greater than 1. So how much greater than 1 is too big? There's no real definite answer, but we've got a general rule of thumb. If we take the log of the condition number of a matrix, this gives us the number of decimals of accuracy lost. Right, so you can see obviously why we want the condition number closer to 1, because then we're only losing 1 decimal of accuracy. So obviously the larger the condition number, the larger the log of the condition number, and then that will increase the number of decimals of our accuracy that we're going to lose. So let's see what the log of 3,603 is. That gives us 3.6. So we lose 3.6 decimal places of accuracy. And looking back at our original matrix, if we lose 3.6 decimals of accuracy, that's pretty big, because we only got 3 sig figs in our original matrix A, and then in our solution we've also got 3 sig figs. So this system is definitely ill-conditioned, right? Because we've got a large change in A. If we look back when we did the example, we proved it out. Sorry, a small change in A. We've only changed A by 1, right? 1 component by 1 value, and we got quite a large change in our solution matrix, or our solution vector. So when we confirmed it by using the condition number and finding out that our system is ill-conditioned. So that's what it means when someone asks what the condition number is and if the system or if the matrix will be ill-conditioned or well-conditioned. And we found that by multiplying the norms of our original matrix by the norm of the inverse matrix. So there you have it. We've just calculated condition number and the norms and found out if our system of equations or our matrix was ill-conditioned or well-conditioned. So thanks for watching. If you like my videos, please like, subscribe to my channel, share with your friends. There is plenty more content to come.